the topics that I sort of had allowed for this talk, it's a massive amount of material. And so we decided to break it up and go a little bit more in depth in the first part. And then in 2 weeks, we'll sort of finish off. There'll be a 101 and a 102, and I think the algorithm sort of part of this will be the 201 and 202 series, which we'll schedule sometime in the future. So hopefully this will be a little bit of an introduction to a lot of topics, a lot of idioms, but we'll give you guys a lot of depth into the material itself, which I think is probably a bit more beneficial. So let's get started. Who am I? Sabree Blackmon. I'm a security engineer and researcher person. I've been in open source for a really long time. I think I started in doing like open source game development or something, and here I am doing security stuff. These are some of the languages that I use on a regular basis: Rust, Idris, Go. I actually help organize the Go meetup with Paul, who's on the call right now. Interests include type systems and programming languages, which we'll get into quite a bit in this talk. Category theory, formal methods, really nerdy stuff. Previous lives, I've done embedded systems development, software testing, DevOps, AI stuff. And then here's some languages I've used, including VHDL. I did a bunch of FPGA stuff in the past. I don't anymore. I wish recruiters would stop talking to me about it. They won't. It's just one of those things. So that's pretty much me. A little bit of housekeeping before we go too far into it. Definitions are hard, and you'll sort of recognize this throughout the talk. I'm trying to really build understanding from the ground up, introducing concepts gradually, but trying to use Rust nomenclature whenever it's possible. And there are a couple of cases where the Rust sort of naming stuff is not it isn't right. It isn't correct. There's no way to be PC about it. So like things like new types and things like that, which we'll actually talk about in the second part of this, don't necessarily match the definition of like new types in other languages. So definitions are hard, and I'll point out where that is in fact the case. Code is math. Code is a common way for developers to communicate. Let's use as much as possible, but let's not shy away from maths. Effectively saying this is sort of a a data and algorithms talk series, and so maths are going to be a part of what we do. And let's build it up gradually. There's a little bit of type theory here and there, but hopefully I'll do a decent job of explaining it. And if I don't, that kind of comes to the next thing. Ask questions. If you don't understand something, please ask a question, interrupt as much as you want. And this is one of the reasons why I've cut this short, is because I think there's going to be a lot of questions and I want to have time to answer all of your questions. You're never the only one who doesn't get it. So, don't be afraid to raise your hand. I think there's a raise your hand function in Jitsi, maybe. Yeah, I'm not going to see that. So if someone can watch for it, yeah, if someone can watch that and like maybe Paul, if you want to poke me or something,
sure.
Someone's asking a question, I am not going to see that. I'll try because it disappears really fast. Yeah, that's useless. Okay. Okay, cool. But I will try to watch the chat as often as possible as well. So type any questions and I'll try to get to them. Okay, now that we've burned 10 minutes, let's get started. I don't think I have to explain what Rust is to everyone. If I do, I'm very sorry. This talk may not be for you, but I think you will get something out of it. But it may take a little bit longer to get up to speed. But I think most of us know that Rust is strongly typed and it's statically typed, meaning, and those are separate things. Statically typed such that types need to be known at compile time. And it generally works best when the sizes of things are known at compile time too. There are quite a few sort of like cases where it's operating on things where the size isn't known at compile time, like strings, for instance. But that forces us to use pointers, right? And we try to avoid using those for the most part. That's pretty much all I have to say about that. So I guess like any questions before we get into sort of like the type system itself? Any questions about Rust? Sort of like the maybe the agenda? Nope. Cool. So don't be afraid to ask any questions. Okay. So simple types. So Rust has this idea of a primitive type and sort of non-primitive types, but I sort of renamed them simple types, and these are effectively like these are the basic building blocks of all data, meaning these things generally can't get any smaller than what they are. And if you're looking into arrays and structures, they contain simple types, right? So these are sort of the basic building blocks. And so first thing that I'm going to sort of introduce to you, and this may seem very sort of rudimentary, but we have to crawl before we can walk effectively. And so we're going to go over Booleans. Super, super exciting. Booleans in Rust work a little bit differently. Like if you come from Go, for instance, they're a little bit different than how Booleans work in Go as well. And I guess this is sort of also, you're going to see this notation quite a bit in this talk. These are effectively type judgments that are describing the resulting type of, let's call it an expression, right? And so in Rust, true has a type bool, false has a type bool, right? And so these are the two options for Booleans from a literal perspective. Boop. And in Rust, that's effectively what it looks like. Let x equals true, let y bool equals false. And so, Rust does have a system of type inference, so you don't, in your let bindings, have to be explicit about the type. They can figure it out. But you can, tell it. In some places, you have to tell it what the type is. So very, very, very simple. So this is a thing that is maybe a little bit different from other languages like Go, right? Booleans don't have a default value. So they must be assigned true or false before they can be used, right? And so even though Rust will allow you to do something like declare the left-handed bool without giving it a value, if you try to use it, it'll have a compile error, right? It'll give a possible uninitialized variable. And it's just possibly, but it's fairly certain that you haven't actually initialized the Boolean. And so it doesn't initialize the false like it would in other languages, or it's not ambiguous. The compiler actually enforces you to give it a value before you can use it. But they can be made mutable and assigned later, right? So this pattern, left-handed bool, we don't know what the value is, but we want to declare it. So we have this, if statement here. If a person is right-handed, this is completely nonsensical, right? But you can assign different values based on the result of some expression, right? And this will compile. The compiler will know that you're assigning it, and after this if statement, it'll know that left-handed has a value, right, from there on out. So before we go on to anything else, any questions about Booleans? I know they're quite simple, but they are sort of the building blocks for a lot of language. Questions? Nope. Cool. Let's go on to integers. So in Rust, we have the notion of signed and unsigned data, or signed and unsigned integers. And Rust is it's kind of a weird language in that it forces us to effectively state the precision. of the integer that we want to use, it defaults to I32, and we'll go over that in a second. But all of the types have their precision baked in. So there's no guessing, right? You don't have to guess what an int means on this platform, or what a uint means on this platform, or long int or long float. Like, all of those things are actually baked in to the type itself, which I think is quite nice. Signed types start with I, and then the precision, and then unsigned integers start with U and the precision, right? Pretty straightforward stuff. I didn't know that there was a 128, to be perfectly honest. When I started writing, it's like, that's pretty cool. I'm not sure what you could do with that. But the 128 version does exist for integers, for signed and unsigned.
You're future-proofing.
Yes. Which is kind of a like, you can use them now. They're very slow, but you can use them. But yeah, I did find that kind of interesting. So same thing as before. The literal values sort of here are pretty straightforward. If you type 15, it's going to get I32 by default, right? In Rust, we do have this postfix notation, which allows you to attach the type at the end of your number, and that's the type it'll actually use. So things are signed by default, but if you wanted this to be an unsigned 32, for instance, you can just attach to the end, and you're going to get an unsigned 32. Same thing for signed. Say I want this to be a lot smaller because I know we're going to be dealing with very, very small values. You can restrict the result of that using I8. But we also have this prefix notation for literals, for octals, binaries, et cetera, and hexadecimal, hex, octal, binary. And so you can use this in front of your literal to effectively tell Rust this is what the encoding is. And that can be very useful. And then, of course, you can combine both, right? The postfix and the prefix. And it works pretty well. Any questions so far? Cool. All right. And again, this is kind of what it looks like in real Rust.
Excuse me, I have a question.
Yes.
Does the I size or U size, is that default to 32?
For I32 is the default. Or for unsized, yes. So if you if you don't give any sort of notation, it'll default to I32. That's your question?
No, there's I've got some Rust code on my machine, and I've used for like iterator types, I've used U size, and they say that's more efficient. What is that size actually?
Gotcha. So I actually put that's coming up, so I'll talk about it very shortly. But that represents the same number of bits that are available as a memory address on the hardware that you're currently working on. And so, if I'm going to describe the capacity of a string, for instance, that would be in U size, right? So that can actually change. That will change if you're on a 32-bit machine versus a 64-bit machine, for instance. It's more for memory, describing memory and memory capacity. Cool. So back to some Rust code here. I think none of this should be new to most of you. We do have this underscore notation, which are effectively ignored by the compiler. But if you want to sort of represent commas, for instance, you can use underscores here. The one thing that I think is quite interesting, again, if you come from C or C++, if you, we have this let k, which we're saying is an unsigned 32. If we try to assign it a negative number, you'll get a compile time error, right? And so, Rust does have some preventative nature there. Which is quite nice. Oops. There's also some range sort of issues that you can kind of run into when you're working with unsigned. For instance, if you subtract a very, very large number and you get something that is less than 0, there's behavior there that I won't get into too much. But this is just another example of sort of the postfix notation. Some of you may get the dead beef reference. If you don't, be thankful. It's awful. But let's see. Let's go to the next one. So I'm going to kind of describe, this is going to be sort of the pattern for the rest of today anyway. Introduce the type, talk about some of the nuances and intricacies, and then some of the, the idioms that you may not, even if you're, if you've used Rust for quite a bit, you may not necessarily be super familiar with some of these things. All right. I32 max and I32 min will return the largest and smallest signed integers that can be stored as an I32. This can be super, super interesting or super, super useful. So you don't have to calculate it over and over again. And again, this goes back to the Rust type inference. It infers unsigned integer literals to I32. And so if I let I equals 1,000, this will default to I32. And that's true of everywhere, I believe. So floats. This is Rust sort of uses the same IEEE standard as most modern programming languages. It has an F32 and an F64. They are signed by default. And that's really all there is there. Float literals and Rust use the period, but float literals must contain a period. And we'll see sort of like that not working pretty shortly here. But they also support a postfix notation like integers do. So you can, put F32 at the end of your float literal or F64, and it'll return what you expect. Cool. So again, some example Rust code. Nothing super, super interesting here. Again, they are signed by default. The sort of the gotcha here is if you try to assign an integer that doesn't have a period to represent some sort of float, it'll actually throw a compile time error. So if I want to fix this, I could say 96 period. I don't even have to add a 0 at the end, and it will compile. So it'll recognize that as a float. So this goes back to the strongly typed nature of Rust. It's not going to coerce types into other types unless you're explicit about it, generally. There are places where that's not true, but even the basic case of like floats versus integer literals, they are different in the language. And Rust has rational number support in external crates, but the default float behavior will result in round errors. There's a really cool website called that, which is sort of like the meme for float rounding that exists in most languages, to be perfectly honest. But they do have an entry here for Rust that sort of demonstrates if you just use F32 in sort of the naive way without actually going in here and being giving it F32 as a postfix, it'll have that error. So it'll return 0.3 this instead of 0.3. So that's just something to be concerned, to be sort of aware of. The rational ratio crate is pretty well used and reasonable to do this sort of thing. Cool. All right. So any questions about numbers? I know it's not the most exciting topic, but a lot of what we do is numbers. So any questions about the behavior, about, we can go as deep as you want.
I have so many questions about numbers, but
It's a great topic.
well, I do have one question that I've not come across yet, and does Rust have an actual concept of infinity or imaginary numbers yet, or is that do crates exist? I haven't found
Crates. So I've dealt with this problem before, and the crate options are kind of awful, right? So there is in the standard, I think like some new type that represents infinity, but yeah, I don't think none of the standard itself actually uses it. It's just sort of there for other crates to build on. So if you're looking for like imaginary number support, I would definitely look at the crate ecosystem and try to find something that doesn't suck.
Yeah, that's been my problem so far.
Yes. To be fair, right? Yeah, there aren't many languages that have that sort of support built in. But the cool thing is that even if you're using an external crate, you can the numeric is a trait effectively. So even if you have your own custom number traits, your own custom number types, you can put them in places where numeric is accepted. That's a weird detail, but when we go into traits in the next talk, we'll kind of talk about that stuff. Any other questions from anybody else? Cool. So let's go into something a little bit more fun, right? Which are string constants. So if you've used Rust a little bit, you'll know that there's a difference between str string and capital S string. And it actually is one of the more confusing sort of aspects about string handling in Rust that doesn't necessarily have parity with other languages. And so there are a couple of rules here. Any string constant, so anything that's in between quotes, is a string, str. And because the actual contents of the string depends on the length and things like that, you have to use a pointer, right? And so this actually returns a pointer stir, right? You can't really initialize just stir, right? So this will always return a pointer or to a stir or a stir reference, more accurately in Rust. And so just a few examples in Rust. Let name equals John. This is going to return a stir ref, and let y equals stir ref equals ni hao. The cool thing here is that it does support UTF-8, excuse me, out of the box. But because it does, any sort of use of stirs and strings becomes complicated by the fact that characters are not fixed width, right? John uses much less bits than this, right? And so that has some consequences that we'll sort of go into in a second here. So we kind of already talked about this. String constants in Rust are dynamically sized, and it depends on the length and the representation of the string itself, which is why we are forced to use stir reference. The other cool thing is that string constants have static lifetimes, and so if you've used Rust before, that's extremely helpful, right? And although we don't have to use this lifetime marker, we can use it. But by default, any string that shows up in your source code in strings, right, in quotes, is going to be static lifetime. Cool. So any questions about that before we get into capital S strings, which generally what you're going to be using
I won't go too deep into it, but lifetimes are hard.
Yeah, lifetimes are hard. Which is why having a static lifetime, which can be used basically everywhere, is very, very helpful, right? But yeah, lifetimes are hard. But that's not exactly, what we're talking about here. I think, the next half of this talk, we're going to get into async structures. That's where lifetimes definitely matter. So yeah, we aren't going to be able to skip all of that. Any other questions about this so far? Pretty straightforward, I hope. Cool. I kind of purposely left out characters, right? Because they're kind of confusing. Because again, characters in UTF-8, characters aren't the same length, or they're not fixed width, I should say, right? Some characters are actually represented by multiple bytes, effectively. So characters in Rust are a little bit strange, but Rust handles characters the correct way, right? And we'll kind of go into how you can iterate over a string very, very shortly here. And so strings, and again in UTF-8, kind of just listed some important methods here. String from is something that you should kind of become familiar with. It takes a stir reference and returns you a string, right? And then you can also use this method called toOwned, which is a trait on a stir reference, and it'll also give you a string. And you can dereference a string to give you a stir reference, and this is actually kind of helpful later on.
That one I actually didn't know.
Yes, it's really, really helpful that string implements deref. Cool. So a little bit of, again, a few examples here. I want to create a string from John, right? It kind of reads like a sentence, right? And you also use toOwned immediately after a string literal, right? So this will compile. You don't have to do anything fancy to it there. And if you try to assign a string literal to a string, right, it's going to give you a compiler error, right? Because as we know, string literals are stir references. You can't assign a stir reference to a string, right? There's no way to coerce that into a string automatically. You have to use a method. Will there be a recording of this talk? Yes.
Yeah, the talk is actually live on YouTube right now, and as it will remain.
Yeah, which is terrifying. No, it's cool. Which is great because I think the part 2 of this will be also on the channel, so you can watch them back to back, which I think might be actually pretty useful. Cool. So because UTF-8 encoding is kind of weird, right? Strings cannot be indexed. Indexes in Rust are guaranteed to be constant time, which makes sense, right? That's how indexing works in arrays and things like that. How do you do? So that would be the what is that symbol? The asterisk is how, right? The asterisk symbol is for deref, right? Cool. So because indexes in Rust are guaranteed to constant time, UTF-8 can't support that because again, the character width of a particular character is variable, right? And so it may return a single byte one time, it may return 2 bytes to represent a character next time, but it also doesn't really understand that for instance, if you have in your 0 position a character that's 3 bytes and then you have another character that's 2 bytes, how does the index sort of function know that the first byte, the first character is 3 versus 2? it gets really ambiguous as to what you're actually trying to do, and you can't just index over bytes because that'll break some of your characters. But what it does allow you to do, it has this function cars, which returns an iterator. And so you can use this to iterate over characters in your string. And you can use next and all of the other iterator traits, and that'll work just fine. So this is the idiomatic way to iterate over characters. And then this assert will pass. Whoops. The next thing is strings are dynamically allocated. So unlike stir references which point to immutable things, strings can change. I think that is extremely useful, obviously, but the internal buffer that actually stores that string, that internal stir representation, has a fixed size. So if you push new content to an existing string, you may have a reallocation, right? They're pretty efficient, but that does cost something, especially if you're dealing with larger strings. And so you can create a string with capacity, and this is where that usize comes in. And that'll actually allocate the buffer to the size that you tell it to, so you can prevent some of those reallocations in the future. And I think that kind of covers all of our simple types. So any questions about any of the types we just covered? Use cases, idioms, any of that stuff?
No, I'll just make the comment that the paradigm that Rust uses for strings is unlike anything else I've ever encountered.
It's and that's probably worth talking about a little bit more, right? Because I think having a C++ background and having to deal with like wcar and wstring and the nonsense that sort of was that, and then there's fixed width encoding, and there's variable width encoding, and they're not the same. And Rust has effectively said, we're going to make the language opinionated about how we're going to represent language, right? And with that comes a lot of I won't say a lot of complexity, but it's a decent amount of complexity. In Go we have the concept of runes, so anyone who's had to deal with that sort of same thing, it gets kind of weird. But I think Go has, or Rust has made it explicit, for instance, that indexing isn't going to work, so you just can't do it. So a lot of the footguns that you would kind of run into if you were to treat strings as fixed width characters or an array of fixed width characters, it'll kind of prevent you from doing some of that, which is kind of cool. What does gamma turnstile mean? Interpret it just like a bullet. I can elaborate that. So, I think this is kind of important, but also not as important. So gamma here represents the type universe or the type context, right? And so this is called a type judgment. And so this expression, if you want to think of it that way, is of type this, right? But that conclusion is supported by this, which is the type universe, right? You'll see this used in a lot of other languages like DAL, that kind of represent how they describe types. But you can imagine, if Rust had a REPL, right, and I were able to go, to type in string from, some stir character and analyze the type, it would be string, right? And that's kind of effectively what this is saying in a formal language. Hopefully that makes sense. This is called a turnstile, and it's effectively, it's read as is supported by. And so this conclusion is supported by gamma, which is the type universe, or the type context, specifically the type context. Cool. And that'll make a little bit more sense as we kind of get into complex examples, actually. So here, we're going to go into tuples, which are a very sort of large topic, and they're probably going to, I know it doesn't sound like it should be a large topic, but they actually introduce a lot of the complexities of pattern matching and some of the idioms in Rust that actually make it very, very powerful. And so tuples in Rust can have multiple types. And so this is a little bit different than other languages, which force your tuples to have a single type for each field. Rust enables you to have multiple. And so the most basic tuple is the single field tuple, right? And so this 0 just means it's of some type, right? And the tuple of that contains some type is a type. That's really all that means here. But you can have a tuple of multiple fields, right? You can have a tuple with 1, 2, 3, theoretically into infinity, right? Types, right? Which is also a type in Rust. And I will go into some examples here. And so if you have, this is some example of initialization, right? If you have a tuple of true, right? This will actually create a tuple of type bool, right? Because true is of type bool. If you have a tuple of 1, hello, world, right? It'll actually, this matches this type U32 because of the type inference. This is I32, not U32. Oops. Stir reference, right? And so Rust will be able to determine what the types of the tuple, the type of the tuple will be based on inference of the types of the thing it contains, right? So you don't have to be explicit here. And then you can also have a tuple of null, right? And that return, the type of that is itself, right? And so this is like one of the weird cases, but if you've used the result quite a bit and things like that, you may run into this, and it's very confusing when you see it, but it's a thing that you will see sometimes in Rust. Cool. So here's some more examples or some concrete examples in Rust, right? I think the interesting thing here is that we're introducing this type keyword, right? Which allows us to do type aliases in Rust. Type name, =, and then some description of the type. The cool thing here is that tuples, are effectively described the same way as anything else, which is described the same way here as you would if you were to describe it in the let statement. So you could sort of replace it here and call it a couple, and that allows you to reuse this all over the place, which is kind of cool. The other thing that this sort of points out here for couple tool is that tuples aren't lists, right? They have a size, and the number of the type and the elements of the tuple are constant. So you can't change them. So if I try to assign an additional field to this tuple, which should only have 2 elements, it won't compile, right? And that's something that may be different from other languages that you're kind of used to, either because tuples are actually lists, and so you can do something like this, or they're not statically type checked. And the next thing here, just to demonstrate that you can have different types in a single tuple, and Rust will infer the type of the tuple based on what's inside of it. Cool. So kind of went over this. Tuples are statically type inferred. You should never need to write the type signature of a tuple at assignment, even when using custom types. So for instance, here we have a struct person, it has a name, right? If I describe these two people, say I want to capture their age in addition to, their name, sure, why not? I can do that without actually having to describe the type of the new type that we're actually describing here. It'll figure it out for us. I32 person, I32 person. And because this is statically checked, if we assert the type of Timmy and Meg, they should be the same, right? And so this is actually kind of cool because it's one of the few examples where I can create sort of anonymous types that are in fact equal at compile time, and Rust will say, yep, that type checks. This is an I32 person. This is an I32 person. I don't need to name this new type anything. It'll just figure it out for us. So this is another really cool thing about tuples in Rust, is that they automatically get field accessor methods. So .0, .1, .2, yada, yada, yada. And so these accessors reflect the number and order of the field. So the first field of a tuple will always be .0. So it'll always return the first element of the tuple. And so this here is effective saying is if we have a tuple that has type 0, type 1 into infinity, we're going to call it E, right? E.0 will return the type in the first field. E.1 will return the type in the second field into infinity, right? And so that's how the type system is able to sort of figure this stuff out. And this is the example in Rust. So if we have a couple, James and Liz, couple.0 will return James, couple.1 will return Liz. And so we get these things for free. So any questions about that?
I know you're not on the core team, but I just wonder like why a language like Go hasn't implemented tuples.
Yeah, I don't know. But I mean, honestly, I think that actually sort of like looking at the type judgment here may give you a little bit of a hint, right? Because this is the type check of this would be recursive. And that can get very messy and that can get kind of slow. And as far as I know, at least from like the Go type system, that doesn't really exist anywhere else, right? Like you have the things that are variable length are lists or are arrays. That's it, right? And so having a type that can have a length of 100 things that you then have to type check is actually kind of complicated, right? And if I were to, do a .50 on a tuple that has, 100 things, making sure that the type checks everywhere can be kind of slow. So I think a lot of it just comes down to Go sort of is very proud of its compile time speed, and anything that adds like recursive type checking, just, it can get very, very, very slow. Even with something as simple as a tuple. If I had to guess, that's probably why. But I think that kind of comes to the next thing here, which is, Go doesn't also have any real kind of pattern matching. Even C++ doesn't have any real kind of pattern matching, but we have that in Go. And so you may have seen like this idea of let binding or, if let in Go, in Rust. And if you've used pattern matching in Rust, this should sort of make sense to you already. If I have a tuple of type 0 and I do a let binding, right, of that type, and I bind to the first field, say this is a single field tuple, then the type of A should be the type of type 0, right? So it should be very simple. If I have a single field tuple, if I do a let binding against it, I'm going to get the type that's in that single field. But this can be extended into infinity, right? And so for the let binding in a case where you have multiple fields in a tuple is a little bit more complicated, right? And so you can actually use this ... syntax, which we'll go into a little bit, which will effectively say, I want the first thing, and for all the rest of the fields in the tuple, I don't care. Just ignore them, right? So this is a way of binding to the first field. Okay, and so the first field, again, is type 0. But let's say I want to ignore the first field and get the second field, right? I can use this whole, and we're going to get into this a bit more later on. So I just want the second field, right? And then I'm going to ignore everything else. right? And so that should give me the type of the second field, right? And so again, to the point of like, why doesn't Go have this? This is kind of complicated, actually. Type checking this against, say, something like destructuring or pattern matching can get kind of messy, but it enables us to sort of pick out specific fields in a tuple and ignore the rest.
Yeah, I was going to ask, like, and you may or may not know the answer to this, but the actual compile time cost for doing that, like, how high is that?
Yeah, I'm not sure how this is implemented, but again, it is, well, that's not true. So Rust has sort of, they've made their compiler very, very idiomatic, and so a lot of the structure is like a tuple. If you want to get type information out of a specific kind of tuple or specific tuple, in your code, it'll actually give you an iterator, so you can iterate over the types. And so, but because you can describe tuples ad hoc in Rust everywhere, right? Each one of those sort of instances is going to give you a new type of tuple, right? And so you're kind of recursing potentially over each one of them over and over and over and over again, right? Rust iterators are very, very fast. Go does not have iterators, right? But I think the actual sort of compile time cost of tuples over like generics, for instance, it's not even close, right? So from a scale perspective, it's still recursive, but it's not that bad. And so this kind of goes into the destructuring pattern with some Rust code. And this is kind of important because a lot of people, if you go back to sort of the type judgment, this ... is here in this third field, even in the second, so I'm trying to get the second field, right? But it's still followed by comma ... right? And that is kind of weird, but it makes sense, right? The ... pattern allows us to ignore any and all remaining fields. So if there aren't any, it's fine too, right? And so in this case, we have let name equals, a tuple of Toby Fox. The first name, I just want the first name of, there's a typo here. I changed the example, this should be name. This will return Toby, right? If I just want the last name, right, this should return Fox, which it does. You can do multiple underscores, right? And so that's actually a good point. But I'll finish this example. And we have this second line can be rewritten as this, right? And so last name prime ... these should be the same, right? And they are. And so this is useful kind of for future proofing, and I wish more people would use it, because if I were to add an additional name to this tuple, for instance, if I use the second pattern, all of a sudden that breaks, right? So using the ... here allows us to ignore any and all remaining fields. So if that, you can think of it as a schema change, right? This pattern, for instance, won't break if you add additional fields to the tuple. And so can you add multiple underscores? That is a great question. And it's kind of supported, by the judgment here. And so, and this is, these are my own sort of descriptions of the Rust type system, so take them with a grain of salt. But yeah, so you can have one underscore a, so I guess the third example would be a ... in between the underscore and the a to represent more underscores. You can also do that. All of those would work just fine. Cool. And another sort of, interesting little paradigm that a lot of people aren't necessarily aware of is that function parameters follow let binding semantics, right? And so if I have a function that takes a tuple, and this also applies to struct, but that's for the next talk. If I have a tuple of student and bool that represents student pass fail, right? And so I create a new type here. If I have a function that takes a student pass fail, I can actually perform that pattern matching or that destructuring as part of the function argument, right? So I don't have to do that later on. I can do that immediately here. And so I can operate on past. It's a Boolean because this is the second argument, which is bool. So that type checks. Congratulations, student.name, right? And so I can immediately use student and so on and so forth, right? And so this is a very neat sort of way of making this clear. Otherwise, you would have to, I'm not entirely sure how you would do that. You would have to create a new let statement in your function, which is kind of unnecessary. And so the last thing that I kind of wanted to go over with tuples before open up for additional questions. Nope, that was the last thing. Never mind. So the other half that I kind of like cut off is about structures, which are kind of like tuples, except even more complicated. And some of the rules are kind of exhaustive, you can imagine. And then enumerators, which are sort of like the really, really beautiful part of Rust, I think, in my opinion, because you get exhaustive pattern matching across all of those sorts of things. So I didn't want to go into those things to pile on all that information right now. So what I would do is open the sort of open questions for the material that was covered so far, or just about Rust in general, if you have like Rust data or Rust type system questions, as we have sort of the remaining time.
Yeah, so I'm looking just at that that function signature.
Yep.
Are the student and past actually your arguments then?
Yes.
Okay. I never seen that that signature, but I like it.
Yeah. So this is again sort of one of the reasons why I did sort of like spend the time to do stuff like this, because this sort of thing should apply everywhere, right? And so any let pattern match should work anywhere let binding semantics are a thing. And that includes function signatures, and then also includes match statements, right? And so the left side of the match arm follows let binding semantics, right? And so all of those things should be the same. And because Rust is sound and mostly consistent, it also means that it works for arguments, right? And I don't even know if it was intentional that would work with arguments, but it does because Rust is sound, right?
And there was one more question I had on one of the. I didn't actually write down the number, but it was. You had actually, I guess, a struct defined with a tuple inside, or maybe not. I don't remember. There was one that specifically called out a static on the inside, or it was a string ref, but the actual type was not lifetimed, which in my experience, I have to do that, and maybe that's just structs.
Yeah, so that gets kind of weird. So if this were a stir reference, right, then struct person would require a lifetime annotation, right? But we're saying explicitly that this has to be a static string, right? And because it's the only reference that's in person, then it doesn't require an additional annotation.
Gotcha.
Yeah. Yeah, and I think that one of the tragedies, if you will, about Rust as it is right now is that even something as basic as using string literals requires you to understand lifetimes, kind of. Right. Which is kind of annoying, because there is a difference between a string literal stir reference, which will always have a static lifetime, but there's a difference between that and a string reference that you'll get back from a string, right? Because that doesn't have a static lifetime. And even though the types are still stir reference, One refers to static data. The other one that you get from a string does not. So, and then you're like, what do you mean static lifetime? What is that? And then you go down the rabbit hole, and it gets very complicated very quickly.
So the actual string type dereference would be a dynamic lifetime then, or
that's
to the owner of the string?
Yeah. So let's actually let's look at it, because I don't want to lie to you.
I've been down this rabbit hole many times, but I keep finding myself going into it.
Deref. This conversion is very inexpensive. Yeah, so it is tied to the lifetime of the string, which makes sense.
It does, yeah.
Right. But if you're trying to use that where in places that require a static string reference, it's not going to work.
Yeah, like I said, this is the first time I've learned about this, so I don't know if I'm going to use it, but it's good to know.
Yeah. But it's a very easy annotation, right? And so this is like one of the easiest, if not the easiest, to kind of figure out, because strings they generally have pretty clear lifetimes. But if you generate a string from a string literal, that's confusing, right? If you use string from something in quotes, right, then the lifetime of the string is static. Yay, right? It's that can also be wrong. So it's to say for the case of right now that it is the lifetime goes through a change when you go from string from, even if under the blankets there isn't a new allocation. That's weird. But there generally isn't a new allocation if you go string from a string literal. I think the first time there isn't, but any additional times there is. So that would actually sort of be in here. String from it doesn't actually say. Yeah, I'm not sure if that's a guarantee in the language. It probably isn't. So I would not depend on that. Cool. Any other questions about strings? We didn't go over pointers or slices, kind of intentionally, because again, those can get kind of confusing. But I think the next topics that I want to get into are structures, arrays, and enum, and from there we can go into pointers and slices, and then all the other fun stuff.
No, I've learned more about the Rust type system than I ever thought I would in this talk, so I appreciate this.